So in lesson 5.3, we're going to learn the third and last method for solving systems that you learn in Algebra 1. It's called solving systems of equations by elimination. It's probably my favorite, so yeah, just brace yourselves because this might just blow your mind. It's pretty cool. It's not necessarily the best choice for every single system, but when your system is set up in standard form, it's really helpful. So in previous sections, we used graphing and substitution to solve systems of linear equations. Another way of solving a linear system is to use the elimination method. So that's the one we're learning today. Elimination. In the elimination method, you combine the equations together to get an equation in only one variable. Okay, so that's the big idea. And you have a few kind of step-by-step procedures here, but it might not make a whole lot of sense until you see it in action. So let me give you just the overall idea. Okay, when you are doing elimination, it's particularly helpful when nothing is isolated. For this particular method, we don't need anybody to be by themselves. This is, number one is actually in perfect setup for elimination. So we're not trying to isolate anything. Our goal is different here. Our goal for elimination is to have one of our variables have exact opposite coefficients in front. So that's why this is a prime candidate. When I look at my x's, I have a positive 1x on the top and a negative 1x on the bottom. 1 and negative 1 are exact opposites. That is what you want to have when you are going to use this method. Okay, if that's not already there, then we're going to talk about strategies for creating that. But that's really your goal. So our goal is different than with substitution, where we wanted to get a variable by itself, or with graphing, where we wanted to solve them both for y so we could graph them. This, we want somebody to have exact opposites. Okay, now check this out. Like I said, brace yourselves, because this is, your mind, just have your mind blown. It's just a second. It's pretty cool. Here we go. I get really excited. I like elimination. So if and when you are in a situation where you have exact opposites and your like terms, or your the same variable terms, are directly over each other, like you want your x's over your x's, your y's over your y's, and your constants over your constants, then you're ready to go. That's why this is a good candidate for standard form, because check it out. This is what we're going to do. We're actually going to drop a line underneath the second equation here, and we're literally going to combine these guys straight down. We are going to practically, kind of squish this and combine these into a single equation together. And in that process, since these guys have opposite coefficients, one of your variables is going to eliminate. That's the big idea here, is that as I combine like terms vertically straight down, one of your variables will eliminate or cancel itself out. So if we do that on number 1, and I go to combine my like terms, my x's here, positive 1 and negative 1, those cancel out. So the x's totally disappear. 3y and 2y is 5y, and 17 and 8 is 25. And look at that, you guys. Is that crazy or what? You went from having 2 equations with 2 variables where nothing was isolated, and you literally turned that into a one-step equation. Isn't that awesome? And now we can solve for y. We now have just a single equation with one variable, and all we have to do is divide both sides by 5, and we find out our first answer is 5. So y is equal to 5, and then once you know that, now it becomes just like substitution, where we plug that back in to either one of these, it doesn't matter which one, and solve for the other variable. So I'm going to go with the top one, since that x was by itself and I don't have to worry about a negative. So I'll plug it into that x plus 3, and then I'll insert that 5 in there to solve for the other equation, or sorry, the other coordinate. So x plus 3 is 15, and then we subtract, and I get the second solution, which was x is equal to 2. So our ordered pair would be 2, 5. And that is the elimination method. Okay. Now, that one was phenomenal because everything was lined up and set up the way we want it, right? So part of the challenge is to get our system to look like this if it doesn't originally, right? So let's take a look at number 2, for example. So on number 2, first thing I want to check for is, I don't care that anything is isolated or not. What I care about is, do I have my like terms vertically aligned? So I've got x terms, y terms, constants. We're good, okay? The next thing I want to check for is having those opposites, so that when I combine, I want something to cancel. Well, I don't have exact opposites, right? I've got a positive 2 and a positive 2. I've got a 3 and a 1. And neither of those are exact opposites. But it's pretty easy to get those. So, like for example, right here, I think the x's are a really good candidate. I already have the same number. All I need is the opposite sign, right? So I can take one of these and multiply the whole thing, through by a negative and change all those signs, right? So as needed, if we do that, if I went in and said, okay, I'm going to distribute a negative, I'm going to multiply both sides by a -1, that changes this sign, that changes this sign, that changes that sign, right? As long as I multiply through everything, I create that equivalent equation. We had talked about that a couple of times in a previous unit, creating those equivalent equations, right? But this time now I do have my opposites. So I'm going to basically do the negative and the negative and the negative of that. And now I can combine straight down. So as I combine straight down, my x's cancel, because 2 minus 2 is 0. They cancel out. I get 3 and a -1 is 2y. And 10 and a -2 is 8. And check it out, right? We went again from a 2-variable, 2-equation system to a really simple one-step equation. All I have to do is divide by 2. And it turns out y must be 4. And then we can take that and plug it in to either one of the originals. It doesn't matter which of these two you plug it into. Okay, so like let's say that I plug it in to the top one here, and then I can say, all right, now we know that 2x plus 3 times 4 must be 10. And then we can solve that for x, right? So I'm taking that top one and I'm inserting that y value of 4 where the y was, okay? When we solve that, 3 times 4 is 12. We move the 12 to the other side. That gives us 2x is equal to -2, and we divide. And it turns out x must be a -1. So our ordered pair is -1, 4. And that's the solution to the system. If we graphed it, it would be the intersection point, right? We could have done this by all the methods, but this was a really good candidate for elimination because nothing was isolated and your like terms were lined up. So that's usually how you know it's a good deal. Okay, let's try number 3. On number 3, again, check to make sure like terms are vertically aligned, and they are, and then check to see if you have opposites or something close, right? So when we look at number 3, 4 and 1, those are not opposites and they're not really very close, but these guys right here, I have 3y and 3y, so very similar to number 2 here. I have the same number. Oh, I just wish I had opposite signs here. Oh, but wait, I can, right? All I have to do is multiply everybody by a -1 and switch all my signs, right, all the way across. I create an equivalent equation where I have a -1, a -3, and a +3. And now I can drop my line and combine straight down. 4 and a -1 is 3x. +3 and -3 cancel. And 6 and a +3 is 9. And there's my one-step equation. 3x is equal to 9. Divide both sides by 3, and we have our first solution. X must be 3. And now we can take that, plug it into either one of the originals, either one of these here. So let's say we go with the bottom one here. The original was x, which is 3. Just kidding. So if I plug it into the original bottom one, it was a +x, which is now going to be a 3, plus 3y is equal to -3. We'll move this. So that's 3y is equal to -6, and then divide both sides. And it turns out that y must be a negative 2. So our ordered pair solution for this one was 3 comma negative 2. That's your solution. Okay, so that's the elimination method. Pause it here, try number 4 by yourself, and then press play. Okay, so hopefully you tried number 4. Let's do it together. Make sure your like terms are lined up, and they are. See if you have exact opposites, and we do, right? This was pretty nice. We have a positive 5 and a negative 5 already set up, so we don't have to make any equivalent equation changes. So let's drop our line and start combining straight down. So 5x minus 5x cancels. 2y plus 3y is 5y. And negative 28 and 8 is a negative 20. So there's our one variable equation. Turns out y is negative 4. And then when you plug that back in, it doesn't really matter which one you do it in. I'll do this bottom one. So I've got negative 5x, move this over, plus 3 times a negative 4 is equal to 8. So we'll simplify. See if what you got here follows along. You might have used the other equation, which is fine. Just kidding. To solve for x, we'll actually move the 12 first. So that's a negative 5x is equal to 20. And then we divide both sides. And, oh, looky there. It's also a negative 4. So our ordered pair solution is the point negative 4, negative 4. And that would be the solution to that system. If you're unsure, you can always plug those back in, even if you just do it on the calculator, right? Throw your calculator in front of you and put 5 times negative 4 plus 2 times negative 4 and see, make sure it gives you negative 28. And throw in negative 5 times negative 4 plus 3 times negative 4 and make sure it gives you positive 8. Should make both equations true if it really is a solution. So that is the elimination method. Okay, we're going to step it up a little bit to more realistic. So those were fairly nice, even if we had to change the sign. That's all we had to do. These are going to be a little bit more realistic in nature. And so we want to solve the system by elimination. Multiply, if necessary, one or both of the equations so that at least one pair of terms has the opposite coefficients, right? So if you look at number 5, we want something to eliminate. Always check to make sure your like terms are vertically aligned. They are. And then we're looking for those exact opposites, right? So nothing here is an exact opposite. I can always check for things like, well, do I at least have the same number? Or perhaps, opposite signs. Those are always a good place to start, right? But sometimes you'll have to, again, multiply the entire equation through and create an equivalent one to get what you want, okay? So in this example, for example, I have a positive x and a negative x here. So I already have opposite signs. All I need is really a 2 here. So one option I have is to multiply the top equation by a positive 2, and that would give me 2x here. Cancel. Or if you look at your y's, I could do something really similar there. I also have opposite signs. I would need a 2 down here so that these would be exact opposites. So I could take the bottom equation and multiply that by 2 so I could get a negative 2 there. So let's do that one. It really doesn't matter which one you pick, but I'll go with that. So I'm going to take this entire equation and distribute and multiply by 2. We've done this again before with equivalent equations and when we were practicing putting stuff in proper standard. Okay, so I'm not gonna have to mess at all with the top one. The top one is gonna stay the same in this example. And down here, I'm gonna double all of that. I'm gonna multiply everything by 2. So instead of, so 2 times negative 2 is gonna be negative 4x here. 2 times a negative 1 is a negative 2y. And 2 times a negative 19 is a negative 38. Okay. But now I have that exact opposite coefficient. I can drop my line here and combine straight down. 1 and negative 4 is negative 3x. Positive 2 and negative 2 cancel. That was the whole idea there. And then positive 20 and negative 38 is a negative 18. So there's my one-step equation. All I have to do is divide both sides by negative 3, and I realize x must be 6. Once you know that, you can come back to either of these original, it doesn't matter which one, and insert that 6 for x. So I'm going to use this top one, but it doesn't matter which one you pick. So I'll put in 6 plus 2y is equal to 20. Okay, so I'm just taking that 6 and inserting it where x is. And then I just solve for the other variable. So subtract, you get 2y is equal to 14. And then divide both sides by 2. Turns out that y is 7. So the solution for this is 6, 7. That's the solution to your system. Okay, take a look at number 6. On number 6, again, check that your like terms are vertically aligned. See if you already have opposites. I don't. See if you at least have opposite signs, perhaps, and I do. Maybe the y's are a better choice. Really, you could do either one, but I always like to kind of figure out, who's going to be the easiest, right? As much as I love to do math, if I can keep it simple, that's always good news, right? So I'm looking here and I'm like, okay, this actually looks like a really good candidate for a couple of reasons. First of all, because I already have the opposite signs. That's already a head start. Also, because if I want the same number here, I know that 3 can be multiplied to get a 9. So here I could, it's this part right here, guys, think of it like finding a common denominator, right? What's that least common multiple? So can I get these to match pretty easily? Yeah, right. All I have to do is triple this and I'll get the 9. I won't even have to mess with the 9. So that's always a good advantage. For all those reasons, I think I'm going to go for the y value. And what would I need to multiply this whole thing by so that I could get that matching 9? Well, I would multiply by 3. Because 3 times 3 is not, or 3 times a negative 3 is going to be a negative 9. That's what I want to have there. Okay, so again, I'm going to leave the top one alone. On the bottom, I'm going to triple everything. So 3 times 10x is 30x. 3 times negative 3 is a negative 9y. And 3 times 2 is 6. Okay. This method is really nice. Probably the most common mistake that people forget is multiplying all the way through, especially this last one. So if you want to know what's the most common mistake, is people do 3 times 10, 3 times negative 9, but then they leave this at 2. So be really, really careful that you've done all 3 of your terms and that everything all the way across has been tripled. Okay. All right. Now we can go ahead and start combining vertically. So 4x and 30x is 34x. Positive 9 and negative 9 cancel. And 11 plus 6 is 17. So this is my one-step equation. I divide both sides by 34. And I realize x is equal to 1/2. 17 over 34 is just a half. Okay. Once I know that, I can plug that half back into either one of the originals. It does not matter which one. You could do the top one or the bottom one. Let's see. I guess I'll put it on the bottom one. So in this bottom one, I can now write 10 times 1/2 minus 3y equals 2. And then half of 10 is 5. My brain just wants to go there. And minus 3y equals 2. Move the 5 over. And we get negative 3y equals negative 3. And then when you divide both sides by a negative 3, running out of room here, y is just 1. So our ordered pair for this solution is 1/2, 1. That's our solution to the system. Okay. All right. Let's look at number 7, because this is really probably the most common type of realistic situation you might need. Okay. If you look at number 7, you want to eliminate something, right? And as I look at this, we've got our like terms are already vertically aligned, but I don't have opposite signs and I don't have matching numbers. So I really need to decide what I want to do. Well, again, you could do either one, and this really is kind of like finding a common denominator when you're doing that with fractions. Or what it really is that we're finding is that LCM, that least common multiple. So like if I wanted these to match, I'm trying to think of what could I multiply both of them and get them to be the same number. Okay, so right away, hopefully what jumps out at you is like, oh, I could turn these into 12s, right? I could multiply the top by 4 and the bottom by 3 and get this to be a 12 and a 12. In addition to that, you'd also want one of those, not both, but one of those to be a negative, right? So in one of those, top or bottom, you'd want to go ahead and also switch the sign. Okay, we could do both of those things at the same time. The other option is here, right? Same thing, we still have same sign, so we'll have to fix that. And we all don't have a match here. And I'm trying to find what's that least common multiple between 2 and 3. What could I change these to? Oh, well, it could be a 6, right? So I could change these guys to a 6 and make one of them positive or negative. And then I would have my opposite. So this is probably like the worst case scenario, this kind of problem where you really need to change both equations. Okay, so 6 is smaller than 12. Doesn't really matter which one, but I'm gonna go for the y's here. So I am going to aim at making these both, and I need to change the sign on one of them. So this kind of problem, I'll have to multiply both of them and create both equivalent equations, right? So I know that to get a 6 here, I need to multiply this by 3. I need to get a 6 here, I need to multiply this by 2. And one of those I have to change the sign, so maybe I'll make this one the -2. It doesn't really matter. It could be either one, okay? But that'll guarantee me opposite signs. So let's work the top. So when I multiply all of this equation by 3, I get 9x, I get a -6y, and I get a -6. So 3 times 3 is 9, 3 times -2 is -6, and 3 times -2 is -6. Okay, now let's work the bottom one. -2 times 4 is a -8. -2 times -3 is a positive 6y. And -2 times a -4 is a positive 8. Okay, same system, we've just created two equivalent versions, but now we have what we wanted and needed, which is those opposite coefficients. And now I can drop my line down and combine straight down, right? So when I do 9 and -8, I get x. When I do -6 and +6, that cancels. When I get -6 and 8, I get 2. So x is equal to 2. There it is. That's one of our solutions. And now we can just insert that into either one of these originals. I'll do the top one, but it doesn't really matter. You could pick either one and solve for y. So 3 times 2 is 6. I'll move the 6 to the other side. And I'll divide by -2. And I get that y is 4. So our ordered pair is x equals 2, y equals 4. Okay? So that's the method for elimination. This is kind of worst case scenario where you have to change both. You'd be looking for a least common multiple. Okay, I'm going to leave A there. We can practice that one in class if you'd like. I do want to try a word problem here, at least one, and we can do the other one in class. So check out number 9. We'll finish with this. The sum of two numbers is 22. The difference of the two numbers is 6. Okay, so let's think about that. We have two unknown numbers. We can call those x and y. Their sum, that means addition, is 22. So one of our equations could be, okay, two unknown numbers have a sum of 22. There's my equation. Together they add up to 22. The difference of the two numbers is 6. Well, difference means subtraction, right? So their sum is 22, but apparently when I subtract them, the difference is 6. That's my system right there, right? We want to know what are the two numbers. So this is a system for the information we have, and it's a great candidate for, imagine that, elimination, right? So I have things lined up, nothing's isolated, but my like variables are lined up, and I have exact opposites. So all I have to do is drop this line, x plus x is 2x. Our y's cancel, and 22 and 6 is 28, right? And so now we've got 2x equals 28, and to solve, we just divide by 2, and one of our numbers is 14. Okay, and then you can plug that 14 in to either one of these two equations. I'll do the top one. If x is 14 and they add up to 22, let's find out what the other number is. We'll subtract. It turns out y must be 8. So our two numbers are 8 and 14. So the two numbers are 8 and 14. When you add them up, they have a sum of 22. When you subtract them, they have a difference of 6. That's perfect. Okay, so that's one kind of word problem you can use elimination for to solve. We'll try the other ones in class tomorrow.